Hey, welcome everyone to this afternoon's session on quantum computation. So I'm Steve Ryan, mathematician and mathematical physicist, the Center for Quantum Topology and its Applications at the University of Saskatchewan, which is situated on Treaty 6 territory in the homeland of the Métis. So I have the privilege of being able to connect with you from here. I encourage you to acknowledge the land and its peoples wherever you are. So I'll be convening this quantum computation session, which features 3 exciting speakers. And we'll have to watch time closely as there's no break between the session and the upcoming panel session. If you have questions, please put them in the Whova Q&A, and we'll be watching that closely. We may not have time to get to all of them, but the Q&A will stay live, and speakers and attendees can return to it anytime and ask and answer questions at their leisure. So on that note, I'd like to introduce our first speaker, who's here today, Professor Lindsay LeBlanc. There we are. So Dr. LeBlanc received her PhD at the University of Toronto before holding a postdoctoral fellowship at the Joint Quantum Institute of the National Institute for Standards and Technology in the University of Maryland. Dr. LeBlanc is currently Associate Professor of Physics at the University of Alberta and Canada Research Chair in Ultra-Cold Quantum Gases. She's a Fellow of the Canadian Institute for Advanced Research's Quantum Materials Program and is the Alberta Innovate Strategic Chair in Hybrid Quantum Systems. So a great pleasure to have her here. Please join me in welcoming her. And she's going to tell us about Bose-Einstein condensates as a platform for exploring novel qubits.
Thank you, Stephen. And thank you to you and to the organizers for the invitation to speak here today. Like you say, I'm at the University of Alberta, also on Treaty 6 territory, which is a traditional gathering place of diverse Indigenous peoples. Today, I'm going to talk to you about basically combining my background, which is in atomic physics, with some newer work that we're doing in my group, which has a relationship to quantum computing. I wouldn't say that we're building a quantum computer just yet, but it is something that we're thinking about. So I know it's a diverse audience, and so I wanted to start off just, at the very basic level, thinking about, what is important about the quantum systems that we're using. And I like this sort of definition. It comes from a paper on quantum sensing, but it talks about how there's sort of 3 levels of quantumness that one might think about. And, there's the quantumness of this discrete energy levels, which in atomic physics is something that's sort of our bread and butter. We're very good at measuring and controlling those. There's also the idea of quantum coherence, the idea that you can create superposition states in quantum systems, also something in atomic physics that we've done a lot of. And thirdly, you can also think about using quantum entanglement. And this is sort of the resource on which quantum computing is based. And this comes about when we have more than one quantum system. And we can link these two together in this special way called entanglement. So in thinking about quantum computing, there are many different candidates for qubits, and we're going to hear about a few of them today, I think. The one I'll be talking about is sort of the free atom, ion, or molecule, and also artificial atoms. We've also heard in this meeting about solid state emitters and silicon and diamond, for example. Superconducting qubits are one of the leading candidates in the sort of race for quantum computing from the industrial perspective, and even things like nuclear magnetic resonance, or NMR, was one of the first demonstration systems for qubits. And all of these have now both a broad range of people in both academia and now in industry working on different systems, and they all have their own advantages. I'm going to focus today, and I should say, yeah, there are others, so I'm sorry if I've missed your favorite flavor of the qubit, but there's a lot of different systems, and they all display these quantum properties, like I mentioned in the previous slide, and some are better than others at certain ones of these. So I'm going to talk today about that candidate that we work with in my lab, which are atoms. And I want to take a little bit of time to sort of think about why atoms are good quantum systems and why we like them so much. So in listing their advantages, why do we use in particular neutral atoms, which are the ones that we use in my lab, meaning they're not charged, they're not ions, and they're also just single atoms, not molecules. And one of the reasons that they're so great in quantum studies is that they are truly identical to each other. So this idea that we use rubidium, every rubidium atom in the universe is exactly the same as every other rubidium atom. There's nothing that can distinguish them. And we know even from statistical mechanics that there can't be anything that distinguishes them. They're really truly identical. And so the other sort of main advantage is that these systems are really readily controlled. And this comes about because people have been doing atomic physics for over 100 years now. And we really have developed a lot of really good tools to do that. I'm going to talk a little bit about that. Atoms are also sensitive to electric and magnetic fields, which means that it can be difficult to control exactly what their quantum states are, but we also have access to manipulating those. And another advantage is that there are sort of transition fingerprints across the electromagnetic spectrum, meaning that we can make optical transitions between some levels, we can make microwave transitions between other levels, RF transitions. It really spans the whole range, and that gives us access to do things in different parts of the spectrum for different purposes, which can be useful, and also to move between these different parts of the spectrum. The other advantage of the particular atoms that we use in my lab is that there are long-lived ground states. And so that means that, for example, these two states form a nice qubit, for example, because you can hold on to that information for some time. In the absence of environmental factors, the lifetimes here are, orders, many powers of 10 seconds. So it sort of depends how you look, but if, naturally it's like 10 to the 15 seconds or something. So it's just a huge number. Okay, so, neutral atoms and quantum computing, I kind of wanted to just take a little tour through history as I begin the talk here. Neutral atoms, like I said, were really, at the birth of quantum mechanics. It was discovering what the atom was and what it was made of that led us to understand what quantum mechanics was. And then through the many decades of the 20th century, there have been huge advances in AMO physics, including things like atomic clocks, the development of the laser, various coherent control mechanisms. And those tools and that history is really what underlies the kind of physics that we do in my lab today. The development of the laser is key, the ability to control the atomic state. These are all just so well understood, and it's actually fun to crack open textbooks from the 50s and realize we're still doing the same things. So, based on that, in the 80s and 90s, there were a number of sort of key developments that made this technology really accessible. And one of those is laser trapping and laser cooling and trapping, which was developed during the 1980s. And then in 1995, the development of the neutral atom Bose-Einstein condensate in MIT and JILA, the first two labs to demonstrate this. And it sort of quickly exploded to many labs across the world. And while I was a graduate student, it would sort of be, announcements of all the different places around the world that were able to produce these neutral atom BECs. So at the same time, during the 1990s, quantum computing was really taking off. Of course, Shor's algorithms were developed in the 90s. And so people were thinking about, okay, can we take this other new technology of cold atoms that is coming along and mixing that together with quantum computing? And here's just a couple of, papers that I find pretty useful, I guess. One is, particularly for ions, but the ideas are similar, and also how to control cold atoms for quantum computing applications, and sort of starting to think about that. But I would say that during the late 90s and early 2000s, the ideas that came about because of optical lattices, the ability to trap these atoms in sort of a crystalline structure, made the ideas of something called quantum simulation, forgot my close quotes there. That idea is what really took off in the cold atoms community, was thinking about how to make many body systems out of the quantum gases that we were using. And that became a really prominent area of study, and sort of diverged a little bit from the universal quantum computing that people had thought about sort of first in the 1990s. So, and that's my history as well, as that I moved into that space. However, it wasn't forgotten. A number of people kept working on the idea of quantum computing through the 2000s and 2010s. And here's just an example of papers, both in optical lattices and otherwise, thinking about how to control the atoms at the individual level. So this is the key difference between the many body physics that often is discussed in cold atoms and the sort of idea of quantum computing, is that you want to control single individual quantum systems. And so these developments were, kept going. And really in the sort of 2010s, the first paper was 2009, this idea of what was first called a quantum gas microscope, the idea that you could address individual atoms in these optical lattices, was first demonstrated out of Harvard. And more recently, that group and many others have started to develop what they call neutral atom quantum computers, where we can trap, they can trap individual neutral atoms in arrays that actually look a lot like the ion trap quantum computers that have been developed all throughout this period as well. And so using this technology that is now available, we're sort of coming back to this idea of using cold atoms as a quantum computer. And you know, here's a couple of papers off of the archive from this year, I guess maybe last year now, where we're really developing significant quantum technologies and quantum computing technologies based on neutral atoms. And so this is exciting, and it's sort of, you know, this idea that so many of us in cold atoms have been adjacent to quantum computing for so long, we're kind of merging back into it. And so this is sort of the story of my lab as well. And we're sort of, you know, learning a little bit about this space in quantum computing more and more. So I wanted to dive into the physics of the atoms a little bit, about why they are so good for this and for our studies of quantum in general. And this goes back to the idea that we can address many different kinds of energy levels and different states of the system. So in the alkali atoms that we use in my lab, we have different electronic states of the atoms, which I'm representing by these sort of purple fuzzy blobs here. And so we can have transition between these two different levels using optical transitions. So the laser light that we use, in our case, it's about almost 800 nanometers, can make a transition from one of these electronic states to the other. But these levels also split into sort of finer structure depending on the internal goings on of these atoms, which depend, for example, on the angular momentum and the spin of the electron that's involved. So for example, if the orbit of the electron has an orientation in one direction and the spin is in the other, the energy depends on whether those spins are aligned or anti-aligned, for example, and that leads to something called fine structure splitting. You can also have hyperfine structure splitting, where now the nuclear spin of the atom matters, and that interacts with the electron spin. And so you can get differences in energy on the sort of microwave level. So these lower states, and I'll talk about these later, they differ by having the nuclear spin aligned with the electron or the nuclear spin anti-aligned with the electron. And so we get these sort of gigahertz energies. And then even further, we can further split these levels using magnetic fields in the lab. And we can access the Zeeman splitting. And typically this is in the megahertz regime. And so we're able to span this sort of frequency range from terahertz to gigahertz to megahertz, sort of choosing which transitions we want to use and which frequency ranges we can address. And so through this interaction with light and matter, we can develop these interfaces where we can manipulate, control, and measure the quantum systems that we're working with in the lab. So I mentioned BECs in the title of the talk, and we use them for the experiments I'll talk about. And the reason we use them in our lab is that basically, to some good approximation, they're a single wave function that describes a whole kind of mesoscopic system, a system of 10 to 100,000 atoms, somewhere in that range. And basically, you can get a quantum wave function that describes this whole thing. And the way we use it in the lab for what I'll talk about today is actually just as an ensemble of many copies of the same quantum state, because they're all in the same quantum state. And that lets us do measurements of a single system that actually comprise an ensemble measurement. So we have a lot of opportunity to do that. So in the interest of time, I've basically said this already. Here's a picture of our experiment. And we have a number of different focuses in the lab. One is on quantum memory, which I won't talk about today, but we use the optical transitions there to store information in our atomic degrees of freedom. We've also been working with microwave atom optics, where we use a microwave cavity to enhance the microwave transition and simultaneously probe with an optical transition. And then finally, I'll talk a little bit about these unconventional qubits that we've been working on. So the first, and I think I'll only have time to talk about one of these, is the idea of using the various transitions in this atom to basically control the quantum states and understand what we're doing there. So in the first set of experiments I'll talk about here, we're going to think about the geometric phases and something called a holonomy as it relates to quantum computing. So this work is largely led by Logan Cook and Irina Teshlina, a PhD student and postdoc in the lab, with some assistance from others in the lab, especially Joey Linden. And we're also working with some of our theory friends here at the University of Alberta, including student Mason Protter. So the basic idea that we're using here is that the geometric phase, or the quantum mechanical phase of this object, can depend on how we change parameters in space. And we're going to sort of use this idea of, can we look at this quantum system that we've got and we control so well, and figure out how to do rotations through this geometric phase space that can lead to quantum computing like operations. And this idea is not new. There's this nice paper from 1999 really just explaining this idea in some depth. So we're going to focus on something called a holonomy, which is, and excuse my lack of mathematical jargon here. I'm not an expert in this area by any means, but my understanding is that holonomy is the idea of a generalized geometric phase in a non-abelian rotation where basically the states are all degenerate. They all have the same energy, and so a holonomy is sort of the set of all possible loops that you can make in this parameter space that satisfy this condition. And the reason why this is interesting for us is that if we do some kind of adiabatic evolution through a phase space, so like the idea is that we have a Hamiltonian describing our system and we apply it to the state, if we slowly vary the parameters in this Hamiltonian, but then come back to where we started, we do what's called a loop. So in a non-degenerate space where you only have one possible state, if you start in some place and you change your parameters, you have to, if you're doing it adiabatically, there's only one state that you can connect to, and you come back to the same state. So you might pick up a quantum mechanical phase like the Berry's phase, but the actual population of the state doesn't change. In contrast, if you have a degenerate system where you have multiple states that have the same energy, there's a potential for doing these loops, but you can actually change your state as you go from a starting condition around a loop and back to the same point. And this is because you can actually sort of develop a superposition between the different states that are part of your degenerate subspace. And so you can imagine creating, say, a superposition state among these degenerate states. And so I've tried to represent that here with two different possible paths through some space. The physical implementation one often hears about is like in a magnetic field, an equivalent to an Aharonov-Bohm phase. And you might have two different paths through this space, and they could lead to orthogonal superposition states. And in that case, you have the potential for basically a quantum computing operation, like something like a Hadamard gate is sort of the flavor of what we're looking at here. So if you can span all of the space with all of the loops that you have available to you, you have the possibility for a universal quantum computer. And that's the ideas that were developed back in the 90s here. The problem, and the reason why it wasn't really developed over the past 20 years is that it's hard to do these things slow enough before some kind of environmental decoherence comes into play. So to do this, you need some kind of system that has degeneracies. You want a complete set of operations that span the space. And for that, you get some kind of intrinsic fault tolerance because you're doing this sort of topological operation where it's the path of the loop that matters, but not like the speed it took or some deviations from the path. As long as you get back to where you started, you've completed the loop and completed the operation. So there's been a number of demonstrations of this in more recent years. There's some earlier ones in the NMR systems, and more recently, this has become a kind of active topic of research among some people working in superconducting qubits. And here's just a couple of references to that. The way we're doing it in our lab is using something called floquet dressing. So we use the idea that we can periodically modulate our system to create a degeneracy in the system because the eigenenergies of our system basically all average to zero. So by doing a fast oscillation and then averaging over those oscillations, we create a degenerate space. And so this is really what we're going for in our system is, can we create this degeneracy in order to do the non-abelian rotations that we want to do in the lab? So the answer is yes, we can do that. We do it by connecting, in our case, 3 different states to create a spin 1 system. And the parameters that we can control are the laser amplitudes that connect the states, the phases of these lasers that connect the states, as well as an external Zeeman field, which controls sort of the relative energy of these 3 states. And so that's the parameter space that we can vary, is these parameters in our Hamiltonian here. And then everything is multiplied by this Floquet term, which makes our degeneracy happen. So we can do various loops through parameter space by changing the parameters in that Hamiltonian that I just showed. And just how we measure it is that we can do what are called Stern-Gerlach images. So we can project the system into different levels, and they're all magnetically sensitive. So we can actually image using a magnetic field gradient the different populations of the states over time. So here's an example of one of our operations. It looks really messy, but you can see that the data that we're taking, which are these points in the 3 different colors for the 3 different substates that we're using, follow very well, especially at the beginning, the operator that we'd expect, which is from this calculation. We have some experimental uncertainty, which is the bands in our magnetic field control that causes some uncertainty towards the end that kind of accumulates. But overall, I think we're pretty satisfied that we're doing a good job of the operations that we think we're doing and creating the loops that we think we're doing. And notably, you can see that we've gone through a full loop here represented by this one, and we end up in a different state than we started with. And that's sort of showing that we're in this degenerate subspace and ending up in a different state than we started with. We also can show that we have phase control over the system by applying the loop with different relative phases and then possibly putting a different phase reference at the end before we do the measurement. We can shift the phase and it sort of responds as we expect. So we can see a pi/2 phase shift between these 2 operations, which comes from a pi/2 phase shift that we applied to the system. So far we've demonstrated that this Floquet approach gives us the degeneracy we need to do this holonomic operations, and we can measure state populations that match the states we expect. Next up, we'd like to sort of prove that it's truly non-abelian, and one of the ways to do that is by measuring Wilson loops, which are basically doing multiple of these loop operations through space and then permuting their order and seeing if there's a difference depending on the order in which you do them. And of course, as an experimentalist, we're always trying to make things more stable in the lab. And if we can basically increase some powers and decrease some noise, we hope to get sort of more into this adiabatic regime and reduce some of that noise at the end of the experiment there. So I'm going to skip to the end here. I just will flash very quickly. Another project that we're working on related to this is also developing a Qtrit among our atoms, and Joey Linden is leading this after really Irina Teshlina also brought this idea to the lab, and she's been working on it as well. And this is the idea that we're using multiple of the levels in our subspace of the atom to create a 3 sort of part quantum bit that carries more information. And so we're also seeing some nice results related to that. So to wrap up, I'll just say thank you to the group and to all of the people who are contributing to this project and to all the others that we're doing. And I'll have a couple of minutes for questions, trying to keep it on time as much as possible here. So thank you very much.
Thank you very much, Lindsay, for the wonderful talk. Really enjoyed this and love the mathematical connections, obviously. We do have 1 or 2 minutes for questions. Just watching here in Whova. So we have a question, which is, how does one deal with the decoherence effects in the Floquet-Dressed approach?
So, so the decoherence associated with the Floquet dressing. So part of the reason for doing the Floquet dressing is to overcome some of the decoherence. So I guess maybe you're referring to the fact that Floquet dressing in atomic systems in particularly is often causes heating because you're actually adding energy to the system by adding this oscillation. For us, we're doing everything quite fast on the scale of that heating. So that is one way around that. But yeah, it's something we haven't really come into. We haven't seen that decoherence come from the Floquet dressing yet. It's more of the instabilities in our magnetic fields, which is always our excuse for everything, but true.
No, thanks. And then one more that I see here in Whova is, how in principle would one implement an equivalent of a 2-qubit gate?
Yeah, so I thought I had something, but I don't. So basically one can, you can do these operations, but actually the most practical way for doing this seems to be through Rydberg interactions, which is the same mechanism people are using in the neutral atom quantum computing arrays, where the Rydberg atoms, where you use the upper level states that have a large electric dipole moment, and that sort of creates an electric field for the neighboring atoms that then shifts the ability for the neighboring atom to make its transitions. And so you can affect one atom with the other, and so you can affect two qubit gates using that. And the same sort of principles should apply to these holonomic operations as well. And there are papers that are looking at that. And so that would be the next step, I would say. The other thing is, we would need to have 2 separate systems. Right now, we're using a big BC with a lot of atoms to do a single qubit. And we're starting to think about developing these sort of array systems where we can have multiple qubits in nearby proximity to be able to use these Rydberg kind of operations for that purpose.
Well, thanks a lot, Lindsay. I think that's all the questions for now. So I thank you again for this really exciting talk. And I guess we'll move on to our next speaker. So our next speaker is Dr. Matteo Mariantoni, who's an associate professor at Waterloo, where he's based at the Institute for Quantum Computing. Prior, he did doctoral work at the Technical University of Munich and held a postdoctoral fellowship at UC Santa Barbara. At IQC, he leads a team studying superconducting quantum circuits, focusing on micro and nano-fabricated devices, making on-chip resonators and novel qubits, which are then used, for example, to investigate fundamental aspects of light-matter interaction. So please join me in welcoming Dr. Mariantoni, who's going to be telling us about superconducting circuits, quantum probes for dielectric materials.
All right. Stephen, can you see my slides and can you hear me well?
Yeah, both perfect.
Great. Hello, everyone. Thanks, Stephen, for the introduction and the organization for giving me the opportunity to present some of our results at the Quantum Days 2022. The topic of this talk is on how to use superconducting circuits as quantum probes for dielectric materials. So we think this is an interesting and immediate application of superconducting qubits. And although we do not have hundreds of qubits at our disposal, we can use just one qubit to learn a great deal of physics, or the fascinating physics of defects in amorphous dielectric materials. Notably, understanding such defects will be critical to scale up further superconducting quantum computers. All right, so what kind of superconducting circuits do we use in my lab? We use both resonators and qubits. Let us begin with resonators, which is easier to explain. For example, a resonator can be implemented as the parallel connection of a capacitor C and an inductor L, as shown in this sketch here. Classically, this is represented by a quadratic potential. And so if we were to quantize it, we would obtain a ladder of equally spaced states, 0, which is called the ground or vacuum state of this harmonic oscillator, 1, 2, etc. In order to measure one of these devices, we apply a signal through a transmission line, which is typically capacitively coupled to the resonator, 1, 2. This signal allows us to measure, for example, the transmission coefficient S21 as a function of frequency. This results in a Lorentzian curve, which is centered at the transition or resonance frequency FR of the resonator, which is proportional to 1 over the root of LC. So typically in our experiments, we set this transition frequency to be about 5 gigahertz. And so in order to unveil quantum mechanical properties of such devices, that is to prepare them, to initialize them in the vacuum state, we need to cool them down to approximately 50 millikelvin. Although our resonators are superconducting, they are dissipating. Most of the dissipation is due to dielectric loss, mostly in the capacitor, here represented by this resistance R. This results in a finite width of the Lorentzian, which we call the internal quality factor Qi, that is proportional to R. What about qubits? Qubits are a little bit more complicated. However, generally, we can still implement them as the parallel connection of a capacitor CQ and an inductor. However, in this case, we substitute the linear inductor of the previous slide with a non-linear inductor, which is implemented in our case as a Josephson junction, here represented by these crosses. In fact, we can use one or multiple Josephson junctions to implement a superconducting qubit. In this case, the classical potential is a quartic potential, that is, the energy states, the ground state E, the excited state E, etc., are not equally spaced anymore, leading to a non-linear resonator that is an anharmonic oscillator. And these two states will be our qubit. So here you may notice that there are many other circuit elements. This inductor down here can be used to apply flux through this set of Josephson junctions, allowing us to change the transition frequency FQ of the qubit. Similarly, we can apply microwave pulses through this capacitive coupling, allowing us to prepare the qubit, for example, in G plus E. Finally, we can capacitively couple this non-linear resonator with a linear resonator behaving as our measuring apparatus. This makes it possible to eventually measure the probability for the qubit to be in the excited state P of E. And so, for example, we can apply a flux and move from this configuration to this configuration where the transition frequency is larger now. We can then energize the qubit by means of a micropulse, bringing it to E, and then measure P of E as a function of time. This decays exponentially with a time constant T1, which is called the energy relaxation time of the qubit that depends on R. And as in the case of resonators, this R is still mostly due to losses in the capacitor, and in this case also in the Josephson junctions. So this T1 is the topic of this talk, but before doing that, let's look at how one of these devices looks in real life. So this is an actual photograph of one of our chips. It comprises a few qubits. Each of these crosses is a superconducting qubit. If we zoom in this region here, the actual cross is the capacitance CQ of the qubit. If we zoom in further in this region at the bottom, we eventually observe, we see the two Josephson junctions leading to the nonlinear inductance. And this is called an Exmon-Transmon qubit. So here, in light brown, we have aluminum, which goes superconducting below 1 Kelvin. In dark brown, we have silicon, the substrate above which we deposit aluminum to make our devices. If we want to understand T1, let us take a cross section in this direction along this red line and look at it from the side. That's what we would see. In green now we have the silicon substrate above which we deposit aluminum in blue. However, we know that when silicon and aluminum are exposed to air, they develop silicon oxide and aluminum oxide respectively, which are amorphous dielectric materials. This means that our devices are completely encapsulated in amorphous dielectric materials. Now let's take this little window here, which I rotate down here. On the left-hand side here, and this is TEM, tunneling electron microscopy. On the left, we see the lead is associated with silicon atoms, and on the right, that associated with aluminum atoms. And in between this whitish region at the interface is silicon oxide. So let's try to understand the elemental composition. So here in color, we have the same window. So where green is silicon and blue is aluminum. And again, this whitish region at the interface is silicon oxide. So there is a large peak of silicon oxide of oxygen right at the interface, which is on the order of a nanometer. If we were to further zoom in this region, we would see that an oxygen atom pivots between silicon atoms, occupying two possible states, a left state and a right state. And this is what we call a two-level system, or in brief, a TLS. So what is a mathematical model for a TLS? Well, it's a two-level system, so we can, for example, model it as a double well potential, where the left well represents the left state of the TLS, and the right well, the right state of the TLS. The oxygen atom is a particle with mass m, and if we drop this particle at the bottom of one of these wells, it begins oscillating with a frequency, the frequency of the small oscillations, called the attempt frequency, omega naught. Generally, these double potentials are asymmetric, with an asymmetry given by an energy delta. The barrier height V separates the left from the right well, and quantum mechanically, this particle can tunnel from the left to the right well with an energy delta naught, which can be calculated from WKB approximation, and it depends on DNM, the barrier height V, as well as omega naught. The spacing, the distance between D, between the left and right well, in this case is approximately the interatomic bond distance between the silicon and oxygen atoms, which is on the order of 2 angstrom in this case. So these numbers are those we are eventually going to use in the simulations that we will use to explain our data at the end of this talk. So the TLS Hamiltonian using polymatrices is just a sigma z times the offset here delta, and that at sigma x times delta naught, which is the tunneling energy from the left to the right well. All right, so now that we know what is a two-level system, a TLS, let's try to model many of them acting together. So this has been done for the first time in the 70s, goes back to the 70s, and is called the Standard Tunneling Model, or STM in brief. So before actually introducing the STM more in detail, we need to categorize TLSs into different groups. The first group is called quantum TLSs, or QTLSs. So why do we call them QTLSs? So if you take the energy of such a QTLS, HF QTLS, and this energy is larger than KBT, that is larger than the thermal energy of the environment where these TLSs live. Well, in this case, these TLSs are pure quantum mechanical entities, and therefore we call them quantum TLSs. So as it turns out, each resonator or qubit, which is characterized by an electric field E, is coupled to about 1,000 of such QTLSs. The coupling strength G depends on the electric field of the resonator or qubit times the electric dipole moment P of each of these TLSs, QTLSs. So in our experiments at 50 millikelvin, a QTLS is any TLS with a frequency between approximately 1 gigahertz and 10 gigahertz. Since I remind you that our qubit is operated typically at 5 gigahertz, these QTLSs almost resonantly interact with interaction strength G with the resonator or qubit. In the STM model, these interactions are independent. In addition, the STM model neglects interactions between TLSs. And so in this case, the interaction Hamiltonian between each QTLS and a resonator or qubit is given by an interaction strength G times sigma x, which represents our QTLS, tensor with A dagger plus A, which represents the field of a resonator or a qubit. Now, as it turns out, as qubits are characterized by an energy relaxation time, T1, also QTLSs are characterized by such a relaxation time, which is due to the interactions between these QTLSs mostly and phononic modes, acoustic modes in the silicon substrate. So if we want to investigate the complete time evolution of this Hamiltonian, we need to write down a master equation, for example, in Lindblad form. When we do the math, we obtain one of the most important results of the STM, which tells us that the internal quality factor, or better, its inverse, is proportional to the inverse of the root of this quantity, which is basically the pump power we use, for example, to measure a resonator in this case. So I remind you that to measure a resonator, we send a micro signal. This results in a certain number of photons on average at the resonance frequency. So the result of this curve of this function is an S curve. So this is called the S curve of the STM. So if our pump power is very small, that is, this number of photons on resonance is less than 1 on average, then both resonator and QTLSs are in the ground state, vacuum state 0. Under these conditions, the QTLS and the resonator and all the QTLSs can exchange energy, and this results in a significant loss, and therefore a very low internal quality factor QI. On the other hand, if we pump much more strongly our system, for example, in millions of photons, eventually we reach a saturation limit where all these QTLSs are saturated and therefore effectively turned off. So under these conditions, they cannot exchange energy with the qubit or resonator, and that's why the internal quality factor increases dramatically. All right, so now let's make an experiment. So let's focus again on this panel here on the top left. This is exactly the same TEM image I've shown you earlier in the talk. It's TEM on one of our samples. So in this case, we just took a silicon wafer and we deposit aluminum on it without cleaning the silicon wafer. And thus there is a large amount of silicon oxide at the interface, and therefore we expect there to be many QTLSs. So if we measure now the internal quality factor as a function of power, as I've shown in the previous slide, we find an S curve. In this case, the quality factor in what we call the quantum limit, in the quantum regime down here at a single photon, is very low. It's approximately a couple of 100,000. Well, this is very, very low for quantum computing applications. It's extremely high for classical applications, but unfortunately for us, this is still too low. And so what happens if we attempt to clean the substrate before depositing the aluminum film? Well, we can clean the substrate in 2 different ways, chemically or physically. Chemically, for example, we can dip the substrate in an HF acid. This removes most of the silicon oxide, leading to a better interface with less loss, potentially, as you can see here. Similarly, we can physically clean the substrate by heating it up to about 900 degrees Celsius. In this case, oxygen gets dissolved, which means it goes away, also leading to a better interface with less silicon oxide. And finally, we can do a combination of the 2 cleaning methods, which of course leads to the best interface, the cleanest interface here. So in this case, when we measure the quality factor, we get better and better and better results depending on the cleaning we do. So this result is comforting because it tells us that the STM works under these conditions. It confirms the STM. However, suppose that now we want to measure the internal quality factor as a function of time. Typically, it takes a minute or so to measure the internal quality factor in our experiments. So suppose now we want to measure this internal quality factor every minute for, let's say, 60 hours, as in this plot. So let's focus on the blue curve, which is the one with pump off. That is a very low power in the quantum regime. The internal quality factor is typically stable, even though noisy. Sometimes, however, it undergoes wild jumps, sort of telegraphic jumps, which cannot be explained with the standard tunneling model, with the STM. So how do we explain these jumps? One way to do that is to extend the STM to the so-called generalized tunneling model, or GTM. So in this case, each QTLS not only is coupled to the qubit resonator, but is also coupled on its own to a few, up to approximately 10 TLSs. So this, we call them thermal TLSs, or TTLSs, is another group of TLSs. In this case, the energy of a TTLS is smaller than KBT, and so these TTLSs, or thermal TTLSs, thermal TLSs, are thermally activated, and that's what we call them, thermal TLSs. They are basically a classical entity. In addition, the generalized tunneling model does not neglect interactions between pairs of TLSs, in particular interactions between QTLSs and TTLSs. So this interaction U goes as 1/r, where r is the spacing between these entities, these particles, which is on the order of a few nanometers, so it's pretty strong. And so let me discuss briefly about this gamma here. So as I said, the energy of these TTLSs is small compared to KBT at 50 millikelvin. This means that any TLS in the range from a few kilohertz to a few hundred megahertz in our experiment is effectively a TTLS. So they are still TLSs, which means they can still be explained with double weld. However, the particle now can overcome the barrier by means of thermal activation, which is a stochastic phenomenon. So it's a random phenomenon, which can be explained, which goes basically as the exponential of the barrier height. This is basically a random telegraph noise. So to recap, we have a few TTLSs, which are coupled strongly to each QTLS with a coupling strength U, and these TTLSs undergo random shifts. The strong coupling U results in a frequency shift of the QTLS energies, delta F minus plus, which in turn are coupled to the resonator qubit, the coupling strength G, and therefore the coupling between TLSs and QTLSs gets transmitted effectively into the resonator qubit. And so if we have random oscillations, random phenomena here at the level of the TTLSs, this will propagate to the resonator qubit. So in the GTM, parameters such as delta and delta naught and P need to be taken from random distributions as here. So this is the model I will use to explain the data in the next slides. So let's make another experiment, but instead of making an experiment on a simple resonator, let's make it on a qubit. So T1 in color code here, in the color bar, is the energy relaxation time, which again, we can measure for a qubit as a function of frequency, which we can tune, and a time here up to 40 hours. So let's focus on the first top 3 panels, which are experiments. So here we can notice 3 main spectral diffusion patterns. So the first one is called band limited diffusive. For example, the one in this region here, in this magenta box. And so here is a sort of random telegraph noise confined in frequency. We can observe also fast narrow band telegraphic noise, as in this region here. This is quite dramatic. So T1 is really good up at a certain point, and then it becomes extremely bad, and then it becomes good again and bad again, and so on. We can see also that here. And finally, there is a slow wideband telegraphic noise, which is similar to this one, but it happens over across a large frequency bandwidth. So we have a good T1 for over a large frequency bandwidth, and then a bad T1, and so on, and similarly here. All right. So now we want to reproduce this data with simulations. And so we use the GTM with the parameters I explained in the previous slides. And so here in these simulations, what we are doing 3 layers of quantum simulations with a few TTLSs coupled to each QTLS, and then thousands of QTLSs coupled to the qubit or resonator with stochasticity in them. So we randomly generate a number of these plots down here, and we post-select them to match the data to see if we can reproduce the spectral diffusion patterns. And we do, as you can see in these plots down here. Now, this one is not an artificial process. It so happens that it takes 40 hours to make these experiments, but to measure these, to perform these simulations, it takes much less time. And so the simulations allow us to explore much longer time periods, which we cannot explore in the experiment. So sometimes we don't see much in the simulations. That's why we need to generate many of them to match the data. But now that we know this, let's finally try to make a more quantitative analysis. So let's try to manually select a few parameters. So in this plot, we have the effect of a TTLS on a QTLS, on a single QTLS. These are the 3 diffusive patterns. So in the first case, this random telegraph noise, this we expected as a sort of 1/f noise. So it should be due to a number of TTLSs, in this case, approximately 10, with mild coupling strengths. The telegraphic noise, instead, being telegraphic, we expect it to be due mostly to a couple, at most, TTLSs, and that's what we observe here. Then we propagate these effects on to the qubit and for different coupling strands G, and we can reproduce again the results of our experiments. So lastly, one final result of this analysis is that the density of TTLSs, which until recently was thought to be uniform across frequency for TTLSs and QTLSs, it is not. The density of TTLSs is much larger than that of QTLSs. And this is something which is quite interesting, and we want to further understand this concept. In more recent experiments, we have done measurements not only over 60 hours, but basically over 21 days for different power regimes and different detuning regimes, making a complete spectroscopy of these QTLSs, and we will report this soon. And with this, I would like to thank the people who made this project, in particular, Dr. Jérémy Bejonen, my present team members, all the alumni, and all of you for listening. Thank you.
Thanks so much for the wonderful talk, Matteo. It was really excellent. So we have a few minutes for questions. Just looking at Huva. Okay, well, while we wait perhaps for some of those to come in, maybe I'll just ask you about what you were saying at the end. So this imbalance between T and Q TLSs. Do you have a sort of inkling of why this imbalance occurs?
You're talking about the densities?
Yeah, the density imbalance, exactly.
Well, I mean, at this point, the only reason the only reason is because basically we have 1,000 QTLSs, and each of them is coupled to a few TTLSs. So obviously that leads to it must be that the density of TTLSs has to be significantly larger. But we don't have we don't have a better explanation for that at this point.
See. And you said that you wanted to do spectroscopy investigations of this. I mean, which techniques are sort of best adapted to this?
So in the experiments we are just running now, they're very similar to what I've shown here. So we still perform these time series measurements, but first of all, we do them instead of just 60 hours for like 3 weeks. So we take data for 3 weeks on the same device. And this is quite interesting because sometimes things are like very shallow for a long time, like for a week or two, and then all in a sudden these QTLSs start acting crazily, basically. And so, but not only we do that, so all these measurements here were basically done on resonance, let's say. So now what we are doing, we are trying to understand the effect of TLSs, which are not very close to resonance with the qubit, but a little bit further. So we basically do these measurements, pumping these QTLSs off resonance. And so it's what is called a hole burning experiment, if you want. In addition to that, we change the detuning of the pump power, if you want, and also the pump power itself. And so this should allow us to better understand a few of the properties of these interactions.
Okay, that makes sense. And there's a question in Huva, so a comment for you, great talk. And at what powers do you see the loss fluctuations in resonators?
At what powers do we see the loss? So I take it as follows. So yeah, so basically this plot here, I suppose. So actually, let me go back to the pointer. Yeah, so this blue line is basically with no power at all. So it's just 0 power, and which, as I said, we call it the quantum limit. This one is full blast. That is, we apply millions of photons. I would say pretty much. So as I said, what we're doing now is exploring all the power settings in between these two extreme cases. And so I would say with a few tens of photons, you still see wild oscillations. Even with a few thousand photons, we still see quite significant oscillations.
Okay, great. Well, I think that answers the question. Well, I think this is a great time to transition to the next talk. So I just want to thank you again, Matteo, for a really, really exciting talk. So thanks for that. And we'll go to our third and last speaker for this session. So it's my pleasure to introduce Professor Patrick Hayden. So Dr. Hayden received his doctoral degree at the University of Oxford has held the Canada Research Chair in the Physics of Information at McGill. He's currently Professor of Physics and also Computer Science at Stanford University, where he serves as the Director of Stanford's Quantum Fundamentals, Architectures, and Machines Initiative. He's also the Director of the It from Qubit Simons collaboration on quantum fields, gravity, and information. So please join me in welcoming Dr. Hayden, who's going to be telling us about a simple architecture for quantum computing.
Well, thank you very much for the introduction and for the information to speak at this at Quantum Days. I really love the idea of this quantum jamboree, bring people from all over Canada and the world together. I'm going to tell you about this simple architecture. It's joint work with Soonwon Choi and Isaac Kim, who were both postdocs at the time we did this work last year, and my PhD students Noah Shuddy and Kiana Wan. And the basic plan, sorry, one second. Oh, okay. Is to demonstrate to you why this very relatively simple looking architecture with a quantum emitter, some delay lines and routers and a measurement system could actually be a way to build a fault tolerant, if not quantum computer, at least a fault tolerant qubit. And I'll tell you as the talk goes on exactly what those pieces are and what they're supposed to do. But before we get there, let's just review some of the existing approaches to quantum computation. So on the left here, I have the Google Sycamore chip that's based on superconducting qubits of the type that Matteo was just telling you about. Trapped ion processors, very similar to what Lindsay LeBlanc was telling you in the previous talk. And both of those are really quite faithful representations of the circuit model of quantum computation, in which you have some qubits in which there are degrees of freedom, so there are some systems with degrees of freedom that we call our 0 states and our 1 states. And then those systems are interacted unitarily via maybe bringing some of those degrees of freedom into resonance with each other, or applying pulses to the system, that kind of thing. So you get single qubit gates and 2 qubit gates. These systems are really incredible feats of engineering. We now have order 100 physical qubits that can be manipulated, and proof of principle quantum computations can be done. But to scale these up to fault tolerance, it's expected that we'll need about on the order roughly 1,000 physical qubits per logical qubit, and to perform a fault tolerant error corrected quantum computation, say to factor large integers, we're going to need on the order of 1 million qubits. And right now we're at about 100. So there's a lot of work to do. And it's not at all clear how we could scale up these architectures to those sizes, that it's not all going to fit on a single chip. And so people are thinking about modular designs. And I think we really should still be thinking about completely new ideas for quantum computation that don't really look necessarily like these ones, or that don't use these only as pieces. At the most exotic end, perhaps, we have topological quantum computation, braiding Majorana fermions, again, an idea that's a cousin to the holonomic quantum computation that Lindsay LeBlanc told you about earlier. There was some excitement about that a few years ago, in which Majorana fermions were first announced to have been detected at TU Delft. Unfortunately, that result faded away as being actually incorrect. And so this approach, while theoretically beautiful, is still at stage 0, it should be said, experimentally. But there's more under the sun. There are other ways of performing quantum computation that look significantly different than what you might be familiar with. And so one method, I'm actually currently on sabbatical at a company called PsiQuantum here in Palo Alto, and they, in their architecture, measurement plays a truly central role, as opposed, and in some ways a more important role than direct interaction between qubits. And moreover, we don't have, because these are photons and they're flying and they don't exist for that long, there isn't a single stable degree of freedom like the superconducting qubit or the ion that's present and you can point to as containing the quantum information for the whole time. And so that's an interesting architecture. It's quite closely related to what Xanadu, one of the sponsors of Quantum Days, is up to as well. Last year, Amazon put out a proposal for how they would like to build a quantum computer that uses transmon qubits of the type that Matteo was presenting to you. But the transmon qubits are being coupled to linear resonators, to more standard resonators, of which you can put potentially many more on a chip. And so there'd be some kind of division of labor between computation and memory, which is something we're very familiar with in classical computation, but is something that has been, I'd say, neglected on the quantum computation side, in which we've tended to just have a uniform array of qubits that all have the same properties, and we work to manipulate those. What I'm going to tell you about today has aspects of both of these ideas. Measurement is going to play a central role, and also hybrid quantum systems. So a quantum system in which there's not just one type of qubit, but there are multiple types of qubits with different properties, and we'll take advantage of that heterogeneity to actually do something interesting. And so I guess I just told you, the big question I want to address in this talk is how to exploit hybrid quantum systems, at least demonstrate that there's something interesting to be said there. And also, just again, something that we really have to think about, how can we reduce the manufacturing, control, and calibrations requirements ultimately to build a fault-tolerant, error-corrected quantum computer? And I'm not going to claim that the architecture that I'm presenting today is really the way that we should do it, but the real message is going to be that there are axes we can push on, and there are tricks that we can play that have not been explored to date, and that there's room for improvement over what currently exists. So here's the design that I'm going to propose to build a fault-tolerant qubit. Now remember, say in the IBM quantum or Google approach of an array, two-dimensional array of superconducting qubits, where you're expecting to require roughly 1,000 physical qubits per logical qubit. Every one of those is going to have to be individually addressable and individually calibrated and controlled, etc. It's a very complicated machine. So what I'm proposing here, which would essentially be able to do about the same thing, there'd be one quantum emitter. So you can think of that as a quantum dot, or it could be an impurity in diamond, or it could be a transmon qubit coupled to a microwave resonator. There are different options. And then that little artificial atom, I'll call it the emitter, can emit, if it's excited, it can emit into a waveguide. And then we can actually route the excitation, let's call it a photon, either into a first delay line or into a second delay line. And it has the potential to come back, interact with the emitter, maybe another time or two. And then there's a single particle detector. And so this is not a simple device, but compared to 1,000 qubit superconducting or 1,000 superconducting qubit quantum device in a dilution refrigerator, it looks not so bad. Now, if you naively looked at this architecture, you might say, okay, well, clearly there's some kind of memory there. I could have my qubit, I could emit into a delay line, and how long is the qubit state going to survive? Well, how long can a qubit survive in a delay line, right? A qubit in a good optical fiber can survive for about 20 kilometers or so, and that's however far light can travel, or however long it takes light to travel 20 kilometers is basically how good this memory is going to be. That would be the naive expectation. But what I'm going to show you is actually this architecture can have a logical qubit lifetime which grows exponentially with the square root of that lifetime I was just talking about. So, so this is much better than you would naively expect. And it's not at all obvious why that should be the case, but I'm going to try to take you through in the next 20 minutes or so a sketch of why that's true. So we're going to make use of an idea called cluster state quantum computation. So I'll quickly explain what that is. I'll explain how you can use an emitter and delay lines to build cluster states. And then I'll explain why this architecture can actually be made robust. And naively, again, if people who know anything about fault-tolerant quantum computation would normally look at this and say this is a terrible, terrible idea, which is what we thought at first, but it turns out it works much better than you should expect. So in cluster state quantum computation, we're going to have an array of qubits. And so in this case, there's going to be a qubit at every vertex of this lattice, say. So there's one here, one here, one here. And imagine they're initially prepared in the plus state, 0 plus 1 superposition. And the way you make what's called a cluster state is you then entangle nearest neighbors with a controlled Z. What that means is that if two neighboring qubits, this one and this one, with an edge between them, are both in the one state, they acquire a -1 phase, otherwise nothing happens. At that point, you're done interacting your qubits in this architecture for quantum computing, And you then just perform a sequence of single qubit measurements. And what computation you perform, determines the sequence of measurements you should get. And in fact, the future measurements that you perform depend in some way on the outcomes of the ones that you got as you went along. And so that's it. That's all you need for quantum computation. And in fact, this 2D square lattice, as demonstrated by Rasendorf and Briegel, Rasendorf of UBC, about 20 years ago, is universal for quantum computation. And moreover, of course, if you really want to quantum compute, it's not enough to be universal. You want to be fault tolerant and universal. The 3D cubic lattice is universal and fault tolerant. And so if you can do this reliably, then you can do quantum computation. And in fact, you can say a little bit more. This sequence of measurements, which a priori could have been scattered anywhere in the lattice, can be organized, say in the 2D case, into columns. And so you measure the first column, then the second column, then the third column, the fourth, and so on. And so they can be ordered in a simple way. And what that means is that we could imagine just preparing the first two columns of that big 2D lattice. And once we've done that, actually all of the qubits in the first column have already interacted with all the qubits they're ever going to interact with, because they only interact with the qubits in the second column. And since they've performed all the interactions they'll ever participate in, you could measure them at that stage. And once they're measured, they disappear. Now you've prepared the second column, make the third column. Now all the qubits in the second column have interacted with all the qubits they're ever going to interact with. You could measure them, and then they go away. And so you can build up your qubit, your two-dimensional lattice, one layer at a time. And what this means actually is that this lattice required to perform cluster state quantum computation can be a lattice in space-time and not just in space, where one of the two directions in the 2D case or one of the three directions in the 3D case is organized in time. Well, how do you, what is the connection? This doesn't look anything like the circuit model of quantum computation. How do you perform quantum computations in this model? I don't have time to explain it in detail, but the idea is pretty simple. Say once you have a 2D lattice, if you measure a bunch of qubits in the Z direction, that's all of the dots here in this lattice, they basically get removed. And what's left behind in this case is the yellow area. If you measure in an eigenstate of sigma x, that actually basically propagates information from left to right. So it's pretty much like a wire. If you measure in any eigenstates of any operator in the xy plane, those perform rotations in the xy plane, and the composition of those can perform arbitrary single qubit rotations. And so with arbitrary single qubit rotations, you're getting towards quantum computation. So here are some arbitrary single qubit rotations. To finish off universality, once you have arbitrary single qubit rotations, you just have to demonstrate that you can do some non-trivial 2-qubit gate. There are some non-trivial 2-qubit gates. In this case, it actually implements that controlled Z that I was telling you about before. So if you verify these statements that I've said to you very quickly, that becomes a proof of the universality of this architecture. Now, how do you get fault tolerance? Again, this is due to Rasendorf and his collaborator Harrington about 15 years ago. You use quantum error correcting codes. And so what you do, I'm not drawing the individual qubits, but you should imagine they're qubits organized in a 2D or a three-dimensional lattice inside this box here. We're going to measure them from left to right. So time is going left to right. And we encode everything into a planar quantum error correcting code, like the toric code, in the vertical planes of this cluster state. And you could use that circuit description that mapping that I described on the previous slide to imagine how you could encode into a toric code and then perform the necessary measurements and so on and so forth. There's a more native, efficient way to make use of or to perform this topological error correction using the toric code or using the cluster states. But at least in terms of intuition, knowing how to implement circuits and then using the circuits to implement the codes kind of gives you the idea. So using this more native format or more native mapping, Rasendorf and Harrington demonstrated that this model actually has quite a high threshold. It can be quite tolerant to errors, that if every qubit at every in this cluster state gets corrupted with random Pauli noise with a probability 0.58%, you can still perform error-corrected quantum computation this way. And subsequently, improved decoders actually push that number up closer to 1%. But we'll just use the original vanilla decoder for the purposes of comparison in this talk. All right, So that's cluster state quantum computation. How do you connect it to quantum emitters and waveguides? So back in 2009, Linder and Rudolph pointed out that if you have a quantum emitter, which in this case I just mean is a system with two energy levels, 0 and 1, and an additional energy level, the E, which is an excited state, that I can actually drive. And when I drive it, the system will emit, or when it decays, it will emit into the waveguide. So if you perform Hadamard, which is a pulse that will prepare superposition of 0, 1, followed by controlled X, which is this pulsing, which will basically copy the state 0 or 1 into the waveguide as a over and over again, then you'll make a one-dimensional cluster state. And I should say that these pulses in the waveguide, the definition of a qubit is no pulse is a 0, a pulse is a 1. Now, a few years ago, one of my collaborators, Soon-Won Choi, and his friends demonstrated that a very similar setup could build a two-dimensional cluster state and therefore a resource universal for quantum computation. And the variation is the following. You have a quantum emitter that will emit into a waveguide. Then there's a reflection, so that the pulse will come back. It gets to interact with the emitter a second time. So the pulse was created, then there's also an interaction, and then the state continues on its merry way. And then if you want to perform quantum computation, you'd measure at this point. And they demonstrated that this was a universal resource for quantum computation. Why? Well, if you didn't, if you just emitted into the waveguide and there was a mirror and the pulse came back and didn't interact again with the emitter and just continued on its way, you could imagine that's just making a one-dimensional cluster state. And if you like, you could just imagine wrapping that one-dimensional cluster state around as a helix going like this. But because the pulses can interact with the emitter upon, when they come back through it, that gives you a delay and a chance in this cluster state, not just to create the helix, but additional vertical links, these ones right here, right? And so you turn a one-dimensional structure into a two-dimensional structure this way. I'd like to visualize this. Here's Trajan's column in Rome. And of course, there's a story being told that is one-dimensional. You follow it left to right, and it wraps around the column. But the figures at one time, if they reached up high, they could actually touch the feet of figures at another time with a delay. And so the one-dimensional structure is really two-dimensional here. And this just really struck me that something so simple, this little device here, if you could make it and you just put a measurement on the end, would be as powerful as what's being built at Google right now. Now, for various reasons, not everyone is running out and trying to do this, which is just that it's not as easy to make, the various, there aren't very many pieces in this, but it's a bit hard to make them good enough right now. But it's still pretty exciting. And so we asked the question, could this actually be made into a fault-tolerant architecture for quantum computing? And the answer is going to be surprisingly yes. And to understand why, I have to say, I'm going to say a little bit more about how you actually, how you would make the 3D lattice and what the circuit looks like. And so our abstract problem is going to be that we have this control qubit Q. That's the only one that is actually going to be actively controlled, that we're going to pulse. It's the only one that we can do anything to. And then the data qubits, which are just these propagating pulses, and we can't do anything with the data qubits unless they interact with the control qubit. And we can't quite use the scheme that I described on the previous slide. And that's because we want to make this fault tolerant. And in the previous slide, in the waveguide, a 0 corresponded to no pulse and a 1 corresponded to a pulse. The problem with that is that if there is significant loss in the waveguide, you won't be able to distinguish the situation in which there was loss from the situation in which there was a qubit 0 state. And so we want our qubits to be what's called dual rail. Both the 0 and the 1 in the waveguide will correspond to pulses, but the timing of the pulse, early or late, will tell us whether it's a 0 state or a 1 state. And in that case, if there's a loss in the fiber, we'll be able to detect it if we can perform single qubit detections, because we'll just see, well, if there's no pulse, there was a loss. And that's actually hugely advantageous from the point of view of fault tolerance. And that complicates things a little bit. We don't have quite the same primitives that we have available, but it turns out that we can actually effectively implement a combination of swapping the control qubit with a data qubit that was prepared in the plus and a controlled Z gate, one of these phase gates. And the way we do it is by actually a controlled NOT into a 0 of the data qubit and a Hadamard. So these are bits, I'm not going to tell you exactly how to do it, but bits that we can actually, with relatively little difficulty, explain how you could, what the level structure would be required and what pulses you need to apply to make it happen. So here I'm just going to sketch, how you make the 2D cluster state, as I did before. So we'll have the quantum emitter, and then here's the waveguide. And the waveguide, its length is is such that it can contain roughly L time step pulses. So at the first step, there's going to be a C0, so that copies the state of the emitter into the first data qubit, 0 here, and then a Hadamard. And we saw that's equivalent to a swap, and then a controlled Z. So that establishes entanglement between the qubit and the emitter. Now there's a qubit in the waveguide, and we're going to do it again. We do exactly the same thing again, and I'll rewind there. Doing the same thing again gives us a swap with the next qubit coming out, which will be number 2. So we're going to swap the state of the emitter into the 2 position, and then apply controlled Z with the emitter. So we're going to get another entangled edge like that. And we just repeat. And once we do, and eventually one of the qubits in the waveguide is going to come back in contact with the emitter, and that's going to implement another controlled Z gate. And so there's another controlled Z, another edge. And then we do the same thing as before, a swap in, controlled Z and edge. And we just, build up the helical structure this way, the 2D lattice with twisted periodic boundary conditions. And it's not too much of a stretch to see that pretty much the same idea can make a 3-dimensional lattice. All you need now is 2 waveguides. The first one, just like before, will build each layer of the 3-dimensional lattice, and then a second longer delay line that has the property that the sum of the 2 delays is going to be L squared steps. And so after L squared steps, a pulse will come back, and that will allow us to introduce edges, which are the edges penetrating into the direction of the board here, like so. So I won't explain that in detail because I don't have too much time, but there's no real innovation there. It's just you do exactly what you would expect to do. So here's the here's the structure that's the structure that you would build, and the problem is that the whole purpose here was to figure out how to do fault-tolerant quantum computation, and this is actually, it looks like a terrible way to implement fault-tolerant quantum computation, and the reason is just that well, essentially, if you have an error followed by a 2-qubit gate, what could happen is that error can turn into a 2-qubit error. If it started out as a single qubit error, it can become a 2-qubit error. And the whole principle, which kind of guides almost all of the work on fault-tolerant quantum computing circuit design, is that we should avoid gates that propagate errors between physical qubits. That is like a general design principle that is almost universally followed. Now let's look at our design here. The data qubits never interact with each other. They only ever interact with the control qubit. And so an error on the control qubit could propagate errors through the entire circuit. Does that actually happen? Well, let's suppose there was an X qubit, like a bit flip error, Pauli X on the control qubit at this point. What happens when you commute it past all of the other gates to see what the error on the final state is going to look like? That. Half of the final cluster state actually has errors on it. So this looks terrible. This looks like a situation where there's an epidemic, not referring to anything like our current situation perhaps, and there's a doctor making house calls, but the doctor is sick. And the doctor, going from house to house, propagates the illness to almost everybody that he or she visits. Now, so it looks terrible, but if we think more abstractly about the cluster state, it turns out it's not so bad, because the cluster state is the unique +1 eigenstate of some set of what are called stabilizer generators. And I'm not going to say in too much detail what they are, but here are some examples. And so the final state, which is actually made, is the same, won't change if we pre-multiply by these operators here. So I'll pre-multiply by those 2 operators, which are some of these +1 eigens, or the operators for which the cluster state is a +1 eigenstate. And if you remember the Pauli operator square to the identity, what you see is that great big error on half of the qubits is actually equivalent to a single error on 1 qubit. And we can prove a theorem that in this architecture, any single circuit level error actually becomes an error on, at most, or a neighborhood of a single qubit. And so things actually remain local. And we can study, and so you wouldn't have, people think about fault tolerance would have poo-pooed this or laughed it out of the room. It actually works pretty well. We can determine the threshold and compare to Rausendorf. Our threshold is 0.39% for the same kind of noise. That's actually, we expected to pay a price because our circuit is more complicated. The noise can actually go from a single qubit to a neighborhood of a single qubit, but it's not a huge price. It's actually pretty good. And if you remember, we went through some lengths to actually make sure that we could detect loss errors. And so we can actually treat loss errors differently. And so for Pauli errors, just random Pauli noise at locations that we don't know about, we saw there was an error rate that we could tolerate of 0.39%. For losses in the fiber, which is actually for, for optical qubits, the dominant source of error, we can tolerate losses of up to 22%, much, much, much larger. And I'm going to have to end here pretty soon, but I'll just say that we do have to pay attention to the fact that the error rate in the fiber is going to increase as the length of the fiber gets longer. And so that places a limit on how large a code you can make and how good the error correction will be. And that's why we can't have an infinite logical qubit lifetime, but just an exponentially growing logical qubit lifetime. I think I'm supposed to end, so I won't say too much more here, other than to say that this is an architecture in which we can build a fault-tolerant quantum qubit with a constant number of components. Even though there is widespread propagation of errors through the circuit, the effective error model is local, and we're really making use of the hybrid nature of this system, that two different timescales, one associated with the control qubit, one associated with the propagating data qubits, actually control the lifetime of the system. And so if it weren't hybrid, it would be useless. And so I think this demonstrates that there's room for new architectures in order to make progress on quantum computation. And I should end there. Thank you very much for your attention.
Thanks so much, Patrick. That was a really beautiful talk. And, it's inspired a lot of questions for me. Like, for instance, I want to ask you about the use of more general surface codes, for instance, just a sample of things I might want to ask you about. But we are a little bit over time. So I think, I encourage people to, continue using the Q&A. Feel free to post even beyond this session. And, we'll go and look back at what people are asking. But in the meantime, I just want to thank Patrick again for a really, really excellent talk, and all three of our speakers for really, really wonderful talks. So thank you all. It was a really lively session that we had. And I encourage everyone to go to the panel session, which is starting just right now. So thank you all, and take care.